Howdy, Eggs. Welcome to another Earth History podcast. The topic this time is ocean circulation for Earth historians. The reason to cover this subject is that the oceans cover 2/3 of the Earth's surface, and they're a fundamental link in Earth's carbon/climate cycle, both in the present day and in the distant geologic past. Understanding the processes that govern ocean circulation and how they're tied to both tectonics and climate is fundamental to understanding how conditions at Earth's surface have changed over geologic time. Let's get started. I'm going to start with ocean surface currents. Water at the ocean's surface is moved by winds, so to understand oceanic currents, we need to start with some basic ideas about atmospheric circulation. Atmospheric circulation is driven by differential heating of the Earth's surface at different latitudes. In other words, the equator receives more solar radiation per unit area than the poles, so low latitudes are warmer than high latitudes. Starting here with Figure 1, the warm air at the equator, here at this location, rises because it is less dense after it's heated than it was before. As it rises, cooler air from higher latitudes moves in to replace it. So that's this part of the circulation and this part of the circulation. This essentially results in winds blowing towards the equator. Higher in the atmosphere, air is displaced by the rising warm air and it flows away from the equator. That's this stuff up here in the upper atmosphere. As it flows away from the equator, it cools and eventually it sinks back down to the surface. That's this right here. This drives this circulation cell at the low latitudes, and there's one in the northern hemisphere here, and there's one in the southern hemisphere here. A similar circulation cell, driven by density differences due to air temperature, forms at the poles. The poles here, for example in the north, receive the least amount of solar radiation, so they're very cold. The air above them cools and sinks, displacing air away from the poles. In other words, flowing from the poles towards lower latitudes. As that air moves towards the equator, it begins to warm and it eventually rises, and this closes this circulation cell here in the north and here in the south. In between the equatorial circulation cell and the polar circulation cell, a mid-latitude circulation cell forms. That's this right here. At these latitudes, surface winds are expected to blow from low to high latitudes. The presence of 3 latitudinal wind belts in each hemisphere reflects the size of the Earth and the amount of energy reaching it from the sun. Now, winds blowing straight north or straight south are expected on a planet that isn't spinning. But because the Earth does spin on its axis, one full rotation every 24 hours, the winds are deflected by a phenomenon called the Coriolis effect. And the Coriolis effect is simply that. It's the deflection of a moving object, in this case the atmosphere, in a rotating frame of reference. That's the spinning Earth. The result is that the surface winds predicted in Figure 1 are deflected so that they look more like the wind belts seen here in Figure 2. Winds blowing over a world with an unbroken, uniformly deep ocean would be expected to drive ocean surface currents like those depicted by the large arrows in Figure 3. In other words, there would be a wide belt of westward flowing water around the equator, contrasting eastward flowing currents in the mid-latitudes in both hemispheres, and then at the poles, small areas of westward flowing water. However, surface currents on Earth are more complicated because on Earth there are continents in the way, and these continents act to deflect the otherwise expected continuous current belts around the Earth. Let's see what that actually looks like in the present day. This is a map of Earth's surface currents with the modern continental configuration. Let's take a look focusing right now on the North Atlantic. Now remember, on an ideal smooth Earth, there would be a western equatorial current belt, there would be an eastward moving mid-latitude belt, and there would be a westward moving polar belt. In the North Atlantic, this western equatorial current is deflected northward right up through here, and it rides up the coasts of South and North America. Where this current would end up joining the eastward moving mid-latitude belt, it gets turned around and it crosses the Atlantic from North America to Europe, where it gets deflected southward down through here along Africa to rejoin its original equatorial start. This circular rotation in the North Atlantic Ocean basin is called a gyre. Similar gyres form in each hemisphere of each of the major ocean basins. So here's where it is in the South Atlantic, here it is in the South Pacific, here it is in the North Pacific, and there is only one gyre in the Indian Ocean because there is really no large northern hemisphere extent of the Indian Ocean. Now, there is an important difference between the northern hemisphere of the Earth and the southern hemisphere. In the southern hemisphere, the eastward flowing mid-latitude current belt is unobstructed. That's this Antarctic circumpolar current right here. It flows all the way around Antarctica in a giant circle. In fact, you can actually see a little bit of a polar westward flowing current belt as well in this set of arrows, this Antarctic subpolar current. Now, with respect to the functioning of Earth's climate system, the gyres play a critical role in the distribution of solar energy. A given volume of water carries a lot more thermal energy than an equivalent volume of air. So the northward flowing limbs of the gyres, in the northern Atlantic, what we call the Gulf Stream, carry an enormous amount of heat from the equator towards the poles. Without them, the temperature difference between low and high latitudes would be much more extreme than we actually experience. These surface currents do not affect water deeper than about 400 meters. So, does this mean that the deep ocean is stagnant and that it doesn't circulate? No way! But its flow is not driven by winds. Let's take a look at what operates in the deep ocean. Deep oceanic waters, in other words, those below about 400 meters, are driven by differences in water density. Two properties affect the density of seawater: its temperature and its salinity. Colder, saltier water is denser than warmer, fresher water. Therefore, colder, saltier water sinks from the surface into the deep ocean, a phenomenon called downwelling. Alright, so the figure in this slide is a north-south cross-section of the Atlantic Ocean. That's an indicator of this white line here on the little map. The color code of this cross-section indicates the water temperature from the surface at the top to the bottom of the ocean. Now, the first thing you should notice is that below about 400 meters, about this depth right here, the oceans are very cold, just a few degrees above freezing. The second thing is that these cold waters occur at the surface only at the very north and very south of the cross-section. Only here and only here. Here's what this represents. Surface currents carry warm water towards the pole from the equator. That's what we're seeing in these red, very hot waters. At high latitudes, the water that's at the surface here begins to lose its heat to the atmosphere and it begins to get very cold. Cold enough to sink into the ocean depths. In the Atlantic, downwelling occurs in the far north, here, and near Antarctica in the far south, here. The North Atlantic water forms a water mass called the North Atlantic Deep Water, and it flows southward through the Atlantic. So it sinks here, and it flows at depth all the way to the southern part of the Atlantic, where it interacts with another downwelling water mass called the Antarctic bottom water. The Antarctic bottom water is even colder than the North Atlantic deep water, so it settles to the very bottom of the ocean. The black arrows at the top of the cross-section, through here, indicate where surface waters absorb heat and where they release heat, that heat being sourced from the sun. So this region here is where surface waters are warmed, and they lose that energy here and here. Okay, now we have a handle on the processes that drive surface currents, winds, and the processes that drive deep water masses, density. How are these connected? Let's take a look. This map presents what is called the thermohaline circulation of the present-day oceans. This is also sometimes called the Great Oceanic Conveyor. Here's what we're seeing here. The blue arrows follow the path of water through the deep ocean, and the red arrows follow the path of water in the surface ocean. Thermohaline means heat, that's thermo, and salinity, that's haline. In other words, the two factors that control density and drive ocean water movement. Let's start here in the North Atlantic, where most of the water in the deep ocean starts. The yellow ovals that you see indicate areas of downwelling of very cold water. From the North Atlantic, this water flows southward towards Antarctica. This is the path that we saw in the cross-section on the last slide. Deep water from the North Atlantic that rises in the Southern Ocean gets re-chilled so it's even colder, and then it gets fed into the deep water Antarctic Circumpolar Current. That's what ACC stands for. The ACC runs in this direction and comes back around here, and it keeps running around in a circle all the way around the world, around the Antarctic continent. It is water from this Southern Ocean that provides the deep water for the Indian Ocean up through here and into the Pacific Ocean out through here. In the Indian and Pacific Ocean basins, these deep waters slowly rise to the surface via a process called upwelling. Once they are at the surface, they can join the wind-driven surface currents, the red arrows, and eventually they are blown all the way back up into the North Atlantic, where the whole cycle can start again. This constant circulation is like a conveyor belt, hence the name, the Great Oceanic Conveyor. Remarkably, it only takes about 1,600 years, really an instant in geologic time, for water that sank in the North Atlantic to upwell later in the North Pacific. In other words, the deep ocean is constantly being refreshed by cold oxygenated surface waters that are downwelling, so it never goes stagnant or anoxic, at least not in the present day. We'll come back to the subject of ocean oxygenation in a few more slides, but before I go there, I need to provide a few more details about the nature of this deep oceanic circulation. This rather complicated figure is intended to be a schematic depiction of the world's ocean basins today and water circulation through them. Essentially, the present-day ocean basins can be thought of as three branch basins, the Atlantic, the Pacific, and the Indian, that are all isolated from each other, but they're all connected through this master southern ocean that flows around Antarctica. In each of the three branch basins, the bottom water is provided by this CDW right here. That's the circumpolar deep water. So that's what feeds the Antarctic bottom water here in the Atlantic, that's what feeds the bottom water in the Pacific, and that's what feeds the bottom water in the Indian Ocean. Now, here's the important point of this diagram. You'll notice that although the CDW feeds the bottom waters of each of the three branch basins, only one of the branch basins has any substantial contribution to the CDW, and that is the Atlantic. And that's the North Atlantic deep water that sinks in the northern Atlantic and then rides up over the Antarctic bottom water to feed into this CDW. In other words, the primary source of downwelling surface water feeding the entire deep ocean, including the Indian and the Pacific, comes solely from the North Atlantic. This single source was certainly not the situation at times in Earth's past, but it's what we have today given the modern continental configuration. Okay, so the Earth's oceans are constantly flowing as a result of wind at the surface and density differences at depth. The question now is, how does this circulation fit into Earth's carbon cycle? Let's take a look. To understand how Earth's oceans interact with Earth's carbon cycle, we need to understand a bit about how carbon is distributed in the ocean waters. And this is determined by a process called the biological pump. Here's how it works. In shallow sunlit surface waters, here the photic zone, photosynthetic organisms use carbon dioxide and water to create organic matter and oxygen. That's this reaction right here. Carbon dioxide and oxygen in surface waters is constantly being exchanged with the atmosphere, which is the main control on the concentration of these two gases at these depths. Now, when these organisms die, they begin to sink through the water column, eventually entering the deep ocean. That's this process here. As their carcasses sink, they are consumed by other organisms. The organic matter from the surface gets combined with oxygen dissolved in the water to produce carbon dioxide and water. That's the reverse reaction of what was happening up in the photic zone. In other words, respiration in the deep ocean draws down oxygen levels and increases carbon dioxide levels with depth. It is the biological productivity of surface water that essentially pumps carbon into the deep ocean. The dissolved carbon dioxide at depth is eventually returned to the surface when deep waters upwell. Now, it is important to note that if the organic matter is not entirely consumed, it can be buried in the ocean bottom sediments, creating a carbon sink. That's down here. Now, the predictions of the biological pump, as I've described them, work to about 1,000 meters depth. So, from the surface to about 1,000 meters down, oxygen decreases because it's consumed, and carbon dioxide increases because it's being produced by respiration. But at deeper depths, the trends reverse. Something else must be going on. But what? Let's see. This is a diagram of oxygen concentration along an east-west cross-section of the Pacific, so right up through here just north of the equator. The purple and blue bands indicate low oxygen conditions, and the yellow and red colors indicate high oxygen conditions. High oxygen at the surface of the ocean is easy to understand. That's what we see up here. The ocean is in contact with the oxygen-rich atmosphere, and it's constantly getting reoxygenated. The band of low oxygen conditions, centered around 500 meters depth, is called the oxygen minimum zone. So that's this interval through here. This is the oxygen minimum area that's formed when sinking organic matter has been respired, thereby consuming all of the available, or at least most of the available oxygen. So the question then is, where is all this oxygen down here in the deep ocean coming from? Well, remember, deep ocean water is sourced from downwelling of well-oxygenated cold surface waters in the North Atlantic. Essentially, oxygen is being delivered to the oxygen minimum zone where it's consumed from both directions. It's diffused downward from the surface, but is delivered upward from deep oceanic waters that are flowing physically from a different location and carrying the oxygen with them. Now, if the oceanic conveyor slows down, then the rate of oxygen delivery in the deep ocean slows down, and the size of the oxygen minimum zone can expand. This leads to low oxygen or anoxic and high sulfur or sulfidic conditions in intermediate water depths in the ocean. Okay, so the constant delivery of oxygenated water to the deep ocean by downwelling in the great oceanic conveyor keeps the deep ocean from becoming stagnant and anoxic. However, respiration of sinking organic matter can still continue even with the delivery of oxygen. And this results in an increase in dissolved carbon dioxide levels with depth. Dissolving carbon dioxide in water produces carbonic acid, and carbonic acid acts to dissolve calcium carbonate, in other words, the mineral calcite. So what's the big deal? Why do we care about CO2 and carbonic acid? Here's why. The planktonic organisms in surface waters that produce the organic matter that's sinking also produce shells that are made of calcite. and these shells also sink when the organisms die. The result is that the carbon dioxide produced by respiration as the organic matter sinks reacts with the sinking shells produced by the same organisms and thereby lowering dissolved carbon dioxide levels. In other words, the sinking calcium carbonate absorbs and reacts with the increased CO2 levels. The depth at which all the calcite is dissolved is called the calcite compensation depth. Below this depth, calcite can accumulate on the sea floor, but below it, there's no calcite reaching the sea floor to accumulate. The depth at which the rate of calcite delivery is balanced by the rate of calcite dissolution depends on the surface productivity, the delivery of organic matter that's respired to produce CO2 to increase the acid, and the rate of deep ocean circulation. If the thermohaline circulation slows down, more carbon dioxide can accumulate in the water, making it more acidic and dissolving the calcite faster. And the result is a rise in the calcite compensation depth and a change in the type of sediment accumulating on the sea floor. In other words, if the CCD rises, if there's more carbon dioxide in the water, this line here becomes more shallow and ends up here. At depths between where it started and where it ends, you see a transition from calcium carbonate containing limestone sediments to clay-dominated carbonate-free clays. And in fact, this change should sound familiar. It's exactly the change that you saw in cores at IODP that spanned the Paleocene-Eocene boundary. So, as you can see, the rate of thermohaline circulation can greatly influence the type and amount of carbon in the water of the ocean, as well as how much carbon can be buried in ocean sediments, and the type of carbon, whether it's organic or calcium carbonate. So the question now is, how much could the thermohaline circulation have changed over geologic time? Let's take a look at a few examples. The thermohaline circulation today is clearly being influenced by the distribution of continents, but as we know, continents drift and they had some very different configurations in the past. Here are two examples. The first, here on the left, is the early Triassic, and it's characterized by a single supercontinent, Pangaea. The Panthalassic Ocean spanned half the globe and went from pole to pole, but the Tethys, this little blob right through here, was restricted to low latitudes. Now, Pangaea would have obstructed any currents that would have circuited the Earth, like the Southern Ocean does today. And the Tethys would have had no direct source of cold, deep water. This suggests the Tethys would have been very poorly ventilated and that its oxygen minimum zone would have been quite extensive. And in fact, Tethyan deposits from this time period record extensive anoxic conditions that probably contributed to the loss of diversity and the delayed recovery associated with the end Permian mass extinction event immediately preceding this time. Now, the late Cretaceous on the right has a very different continental configuration. In this configuration, equatorial waters could flow westward all the way around the world without obstruction. You can follow these red arrows all the way around from one side of the globe to the other. In addition, high latitudes, both at the North Pole and the South Pole, were largely landlocked, greatly limiting areas for cold water downwelling to ventilate the deep ocean. The narrow ocean basins of the Atlantic through here, and the Tethys through here, and the slow thermohaline circulation caused by a lack of high-latitude downwelling may have contributed to the oceanic anoxic events, the OAE events, that are characteristic of the Cretaceous. These are two examples of how different continental configurations may have affected oceanic circulation and correspond to different kinds of global climate conditions. However, changes in climate, especially in solar insolation, that is to say the energy that drives the whole ocean circulation system, can also influence the size and properties of deep ocean water masses. Let me show you. The upper portion of this diagram depicts oceanic circulation in the Atlantic as it occurs today. Hot water is brought along the surface along the Gulf Stream. Here, where it cools in the North Atlantic, it sinks to form the North Atlantic deep water. This penetrates quite far south into the southern hemisphere, where it overrides even deeper water produced as the Antarctic bottom water. Now, these different water masses have distinct chemical signatures, as indicated here by measurements of their stable carbon isotopes. So this is the North Atlantic deep water, and this green tongue it overlies is characteristic of Antarctic water. Now, in this case, the carbon isotopes don't really have very much to do with, for example, the temperature of these different water masses. They're simply convenient chemical fingerprints for different sources of water. But the cool thing about carbon isotopes is that they can be preserved in sediments on the ocean floor. So if we can go back to sediments from, say, 20,000 years ago, during the last glacial maximum, we should be able to map out the deep water masses of the Atlantic back at that time. And that's what's shown in this lower diagram here. You'll notice that the Antarctic bottom water extends much further north into the Atlantic, and that there's not really a North Atlantic deep water, there's what's called the glacial North Atlantic intermediate water. It's not as deep and it's not as extensive as the modern North Atlantic deep water. In other words, 20,000 years ago, during the last glacial maximum, something was different about oceanic circulation that slowed down the rate of downwelling or deep water production in the North Atlantic. Since the North Atlantic deep water today is the source of deep water throughout the oceans, a decrease in the production of this water could have substantially lowered oxygen levels and resulted in shallower calcite compensation depths just 20,000 years ago in Earth's past. Okay, so let me finish this up. The point of this podcast was to introduce you to the rudiments of ocean circulation and how it interacts with tectonic and climatic processes. As Earth historians, we're interested in how the Earth system operated in the past under different conditions than the present. As you will see in class, the tectonic evolution of the Earth has influenced oceanic conditions and, through the oceans, atmospheric and climatic conditions. Understanding the basics of oceanic circulation is instrumental to understanding these changes. So, to close up, thanks for listening, and I'll see you in class.